Chapter 2, Think and Explain Problems. So we have problem 38, and hopefully I've circled all the correct ones that we're discussing that are actually assigned in the homework. A ball rolling along a floor doesn't continue rolling indefinitely. Is this because of seeking a place of rest or because some force is acting upon it? This is a case of, trying to understand Newton's first law. An object in motion will stay in motion unless acted on, will stay in motion at a constant velocity unless acted on by some outside force, net outside force. And in this case right here, if there's no additional forces acting on it, if there's a completely balanced force or no forces acting on it, then the ball would continue indefinitely. But the fact that the velocity does change, so it slows down, which means the speed changes, which means the velocity changes. If it's slow and if the velocity changes, there has to be a net force acting on it. And so yes, there has to be a force acting upon it. It does not seek any place of rest. That's a very Aristotelian kind of view of it, which is been debunked. There's lots of demonstrations. They're done in class and everyday life. Now, identify the force. Now, what happens when something rolls is that there is some slight slipping that's going on there. If it's a perfect roll, it would go on forever. But in reality, the material that the ball is sitting on is going to flex some. It's not going to be necessarily something that you can see, but it will flex some. And that little bit of flexing means that there's going to be a little bit of rubbing between the two surfaces. And so the force acting on it is actually going to be friction, assuming that now, one other thing is it doesn't state this, it is assumed. The floor is assumed to be horizontal. If the floor isn't horizontal, take an example like that, if the ball is going like this, then the force slowing it down, the major force slowing it down would be the gravitational force or its weight. If it's going like this and slowing down, well, then you got some major friction or something else going on there. That'd be kind of strange, but I've been in cars that slow down going downhill. So it's called buying a cheap car. Now, so in this case, though, we assume that we're talking about a horizontal floor. Not that I've ever lived in a house with all floors horizontal, but we pretend. So there has to be some friction, and there is some slight slipping at a potentially at a microscopic level. And we'll talk about more in detail with friction in chapters 4 and 5. Problem 43. Asteroids have been moving through space for billions of years. What keeps them moving? There's nothing to keep them moving necessarily. Now, they are pulled by gravitational, they are affected by the gravitational forces from everything else, just like we are all affected by gravitational forces. But for the most part, once it starts moving, there's nothing that's needed to keep it moving. 45. In doing the tablecloth pull demonstration of inertia in figure 2.4, why is it important that you pull slightly downwards when you attempt to whip the cloth from beneath the dishes? What happens if you pull slightly upwards? Yeah, that's a lesson learned. I was doing that in class a couple years ago, and I pulled up slightly and knocked the water over, made a mess. So you pull down. If you're pulling up, then basically what's happening is you now have, if you think about the forces acting on, so if I have something on the surface and I'm pulling it like this, if I pull up on it, then I'm lifting it off the table. And I'm adding a torque to it, and that adding additional torque. But if I'm lifting it off the table, well, if we think about the forces acting on it, I have weight acting down, I have normal force acting up, and if I increase the normal force acting up, then, well, actually, if you increase the normal force acting up, then you're actually increasing the friction force, which means you're going to have more drag and therefore more torque. Pulling downwards, you're not changing the normal force, therefore the friction is not changing. And so the trick is when you're doing it, you need to pull it quickly so that even though I do have friction force acting on the object as it's being pulled, I want to make sure that that acts on it for such a little bit amount of time that it doesn't have a chance to really be affected greatly. 46. In tearing paper towel or a plastic bag from a roll, why is a sharp jerk more effective than a slow pull? I think there's a video in the chapter 2 additional comments, video that Hewitt does where he demonstrates this. But this is an inertia thing. If you pull slowly, then you're applying a force for, well, one, everything has a breaking point. And so if the force you're applying does not exceed the breaking point, then you'll be applying a force for a long time and it's just going to continue rolling. If you apply a great amount of force, then you're going to hit that breaking point and that force will not be applied for any significant amount of time and it will not roll fast. Number 50, consider a pair of forces, one having a magnitude of 20 newtons, the other a magnitude of 12 newtons. What's the strongest possible net force for these two forces? What's the weakest possible net force? So I have two forces I'm adding together. Vector addition we're talking about here. If they're in the same direction, they're helping each other. So that's when I get the maximum. And so that would be, so 20 and 12, so 32 newtons if they're in the same direction. If they oppose each other, then, well, forces acting against each other, that tends to weaken the overall effect. We're not talking about, we're assuming that you're applying the pair of forces, that these two forces are not going to rip anything in half, that the object itself will stay whole. So, but if I have these two forces acting against each other, then, make one of the directions positive, one's negative. So I got positive 20 and negative 12. Add them together, I get 8 newtons. If I make the 12 positive and the 20 negative, then I end up with negative 8 newtons, but the net force is still, the magnitude of the net force is still 8 newtons. The minus sign is just a directional thing. Number 59. Can an object be in mechanical equilibrium, man, I have difficulty with that word, when only a single non-zero force acts on it? Mechanical equilibrium, as opposed to thermal equilibrium and a couple other catchphrases that scientists use out there. Mechanical equilibrium, or what physicists really should say is equilibrium, is the total force is zero, or the acceleration is zero, or the change in velocity is zero. I'm not saying velocity is zero, just saying the change is zero. So the total force is zero. So if I have a single non-zero force acting on it, I can't have a single non-zero force act on an object and it be an equilibrium because I can't add that. I'm adding it to anything, and so the total force is zero. Total force is not zero, therefore cannot be an equilibrium. 65. For the pulley system shown, what's the upper limit of the weight the strong man can lift? Now, this comes down to what is the strongest force that he can apply to maintain it staying up, or does he just need to get off the ground temporarily? Those are two different questions. If we're talking about equilibrium, which is the intent of the question, the wording is, fuzzy, but he wants to lift it and hold it up, then the maximum weight has to be his weight. The maximum weight he can pull has to equal his weight. Because the force he's applying pulling down on the rope, and so if he pulls with 100 newtons down on the rope is pulling up on him with 100 newtons. That's Newton's third law. He pulls down on the rope pulls up on him. Well, if we think about the forces acting on him, he's got normal force up, there's a tension on the rope acting up on him, and then weight acting down. So the more the tension is up on the rope, the less weight, the less normal force there is. And so if the force pulling up on him from the tension equals his weight, then he's in equilibrium. But the normal force is zero at that point. If the tension acting on him is greater than his weight, then he will actually accelerate off the ground. Now, as he pulls, so let's say he weighs 200 newtons. That's a small kid. Let's say he weighs 2,000 newtons. That's a big guy. My weight is about 1,000 newtons. So let's say he weighs 2,000 newtons. He pulls on the rope with 2,400 newtons. So the rope pulls on him with 2,400. Therefore, the net force on him is 400 newtons. He has net force upwards. He will accelerate upwards. Now, the force on the other side is the rope. We assume that the tension on the rope is a constant magnitude throughout, and so therefore the rope is pulling with 2,400 newtons on the weight. Now, if the weight of the object is 2,200 newtons, then there's a net force of 200 newtons up. That weight will lift off the ground. They will both lift off the ground. At some point, he's either continuing to scramble up the rope and continuing to apply great force, and at some point he'll reach the top, or if he stops pulling, he's just going to sink back down to the ground. So, well, actually, it depends upon if he's holding on to it. If he's still holding on to the rope, actually, if he lifts that weight off the ground and he just holds on to the rope, he will actually rise with the rope as the weight falls back down. It will not stay lifted. Now, if we want equilibrium, we basically need the force that he pulls on the rope to equal his force, which will equal the force of the weight on the other side, and so it can't exceed his weight. 67. A force of gravity pulls downward on a book on a table. What force prevents the book from accelerating downwards? Again, if it's in equilibrium, then it's not going to accelerate. And so it is a book on the table. In class, we call this the normal force. It is a support force. It's the force that keeps one object from going through another. For you purists, or for those who really want to know more, it's an electromagnetic force. But for right now, we just call it the normal force. 73. You pull horizontally on a crate with a force of 200 newtons. It slides across the floor in dynamic equilibrium. How much friction is acting on the crate? Now the vocabulary here, dynamic equilibrium. Equilibrium means the total force is 0. Dynamic means that the speed is not 0. So this object is sliding, so that's the dynamic piece. It's in equilibrium, so the total force has to be 0. So if you're pulling 200 newtons this way, there's got to be 200 newtons going back the other direction in order to stay in equilibrium. And so since we don't know anything else going on in the problem, there's got to be 200 newtons of friction force. And then 78, a child learns that the Earth is traveling faster than 100,000 kilometers per hour around the sun, and in a frightened tone asks why we aren't swept off. What's your explanation? Well, my explanation is that the kid's also traveling along with the Earth. We're pulled towards the center of the Earth. That's the gravitational force or the weight. And so that's why we don't go off of it. But it's not like there's this wind in outer space that's brushing against us. We're traveling with the Earth at 100,000 kilometers per hour as this thing is going whipping around the sun. The other question is 100,000 kilometers per hour relative to what? And so when you start talking about how fast things are going, it is always relative to something. So we've got to be careful about the language there. There is only one absolute speed, and that is the speed of electromagnetic wave in a vacuum. So we're not swept off because we're also traveling just as fast. We don't feel the wind through our hair because the wind is traveling. The air molecules, the things that cause the wind, are still traveling basically at 100,000 kilometers per hour. It's just some subtle differences that we notice, but there is no ether wind, which is something that shows up in a much later chapter. And that's it for I believe that's the Think and Explain.